Okay, we'll go ahead and get started, everyone. Usually people trickle into this meeting within the first 15 minutes, so we'll just allow the tricklers to come in. But thank you all for being here. Welcome to the Great Salt Lake Tech Team. I feel the need to announce what this meeting is because there are so many. But this is the Tech Team, so appreciate you all being here on this chilly December morning. So we'll go ahead and get started with some introductions. I'll start. I'm Marisa Weinberg. I'm with the Division of Forestry, Fire, and State Lands, and we'll just go around the table.
I'm Molly Blakowski. I'm presenting today some of my dissertation work from Utah State University Department of Watershed Sciences.
Sam Lopez, PhD student at the University of Utah, and presenting some of my work on my dissertation as well. I've worked with Bill Johnson over at the U.
Give us the topic, please.
Oh, it's more or less assessing metal sources to Great Salt Lake sediments and tracking metal inputs to the lake over time.
Blake Bingham, Water Rights. Tim Davis, Deputy Commissioner for the Great Salt Lake.
Willie Lanier. I'm with the Utah Department of Health and Human Services, enjoying one of Lynn's cookies.
Linda Freitas, Friends of Great Salt Lake.
John Webb, Wildlife Resources.
Anna Bill with the Nature Conservancy.
Rainward Spa, Utah State University.
Jennifer Bates, Division of Forestry, Fire, and State Lands.
You, Ryan.
Ryan Doherty, Cargill Salt.
Laura Vernon, Water Resources.
Andrew Ruppke, Utah Geological Survey.
Bill Brown, Branch Cooperative.
Banner, Utah Geological Survey.
Yeah, and we, per usual, have a lot of online attendees at this meeting. I will just read down the list. I'm not totally sure everyone's affiliation, but we have Allison Denitis, Amanda Smith, Annie Putman, Carly Beadle, Chris Klein, Christopher Merritt, Danielle Aziz, Heidi Hoven, Jeff Demblecker, Jack Ray, John Uri, Kim Coburn, Lauren Head, Lisa Welsh, Mike Conover, Rob Dubuque, Rob Hartman, Rye Weber, and Susan Zaracarizi. So thank you all for being here this morning. I'll go ahead and just give a few quick updates on all of our different Great Salt Lake groups. So first on the list, Great Salt Lake Advisory Council, which many of you also attend, so I apologize for the repetition. Our next meeting will be on January 10th at the Eccles Wildlife Center. Another meeting that's open to the public, and everyone is welcome to attend and bring your friends. We're always happy to have a full room. Just some project updates with the Advisory Council. This fiscal year, we contracted with the USGS to fund the Great Salt Lake volumetric and area estimate study with Casey Root. So as you might remember, that was a tech team project that was passed on to the Advisory Council for funding. So that project is underway. We also just completed the Great Salt Lake Enhancement Projects project, which I love to call the Projects Project. And many of you were interviewed for that project, so thank you so much for your participation in that. It was a really fast and fun few months getting that put together, but our friends over at SWCA did an incredible job, and that project list is now in draft form and will be released at our January 10th GSLAC meeting. So if you're interested in looking at that list, definitely come to that meeting or tune in online and you'll hear a lot more about it. So thanks again on that one. The Advisory Council also helps fund maintenance fees for the HydroMapper website, which I'm sure you're all familiar with. And another project we're currently working on contracting is a water conservation toolbox, and we've partnered with the Division of Water Resources, and we're hoping to get that contracted and going here in the next couple months. So that's all for the Advisory Council. The Salinity Advisory Committee, typically Ben gives these updates, but he is a ghost this morning. I don't know where he is. So I'll go ahead and give a brief overview of what the Salinity Advisory Committee is up to. Contemplating changes to the berm, assessing how the berm currently is and how it's changed over the course of the summer when we raised it back in February. So more to come on that. I won't get into too much detail because again, that's kind of Ben's brainchild.
What is the salinity now in the south end?
Does anyone have that figure off the top of their head?
A bit under 140 grams per liter. There's a little bit of stratification. Some of the recurring flow is diluted the top meter.
Thanks, Bill. Yes, the next Great Salt Lake Advisory Council meeting is January 10th. January 10th. And if you're on the listserv, you'll get my annoying emails about it. So look out for those.
No, they're good reminders.
Thanks, Anne. Appreciate it.
So the January 10th and the January 10th meetings aren't going to conflict.
Because it's 3.
Did you say the Salinity Advisory Committee?
No. So January 10th is just advisory council.
Okay.
Yes. And the project, which I may have mentioned the date was that they're presenting at that meeting and we'll be releasing the project list at that meeting.
You didn't say when the next Great Salt Lake Salinity Advisory Committee meeting would be, did you?
I believe it's going to be January 25th.
Oh, okay.
Usually those change here and there depending on need, but currently calendared at January 25th. Thank you. So, great. So if Ben decides to show up and he wants to give more salinity updates, I'll let him do that. But I'll go ahead and move right on to tech team updates. So I'm sure you're all curious to know about how we're going to go about our fiscal year 25 grant cycle. A lot of things are still being discussed internally. It's our intention to hold on to those hot topics that we released last cycle. We believe that they were broad and comprehensive enough to capture the same research needs we have on the lake. So it's our intention to just renew those with this upcoming RFP. Again, it's my wish to get that RFP out as quickly as possible. So all of you guys that want to submit proposals can have ample time to do so, and we can get you contracted long before the funding becomes available. So it's our intention to get that even quicker than last year. Some reminders with the fiscal year 2024 grants. If you were awarded a grant, just a plug, those final invoices are due before June 30th. We've had issues in the past with, people have different billing cycles than us. Unfortunately, we operate on a July to June cycle. So get those invoices in. If you have any issues, definitely reach out to me. I'm happy to help you. And another plug for your final reports. Those technically are due at the end of June every fiscal year if you were awarded a grant. Obviously, with people getting published and having different research cycles, that becomes complicated, but that is a requirement with your contract. So if you have any issues, reach out to me, but otherwise, looking forward to reading all of your reports. And one more thing, still missing some fiscal year 23 final reports. So if you are one of those people, send me an email. So that was a lot. If anyone has any questions about any Great Salt Lake meetings or anything that you think of later, call me, text me, email me. Happy to help you out. So with that said, we have two really great presenters today that I'm very excited about. So we'll go ahead and start with Sam, who already introduced himself and what his presentation is going to be. But Sam, I'll let you go ahead and take the invisible microphone.
Sure. Do I need to have my computer on? Do I need to have the mic on my computer turned on, or will it just pick up?
No, those like weird tower-looking things will take in your voice. I'm a little bummed that Keith didn't show up today. Keith was the one that emailed me and said, "Please, can Sam speak at the tech team?" And I said, "Yeah." But very excited.
Me too. Did that work?
You might have to, Molly had it dialed. You shared your whole screen and then you did presenter mode.
Yeah. Oh, I see. Okay. Technologically challenged here.
While we're waiting, thanks, Lynn, for these star cookies.
You're welcome. Is this being recorded?
Yes.
Yes, good.
And the Christmas ornaments.
Or earrings, necklaces, you know.
Great. All right, I think we're set here.
If you don't mind, keep that slide, and then that won't cover your.
Thanks. All right, cool. Hi, everyone. Yeah, I'm Sam Lopez. I know I briefly introduced myself at the beginning. I'm a PhD student at the University of Utah. I'm going to be talking with you today about a couple projects related to mercury and trace metal sources to Great Salt Lake, as well as potential impacts of invasive species removal on methylmercury production in Great Salt Lake wetlands. So a little bit about me at first. I did briefly introduce myself. This is a little redundant. PhD student at the University of Utah. I work with Bill Johnson. He's my advisor. I'm a pathways hydrologist at the USGS Water Science Center. And yeah, I guess I like to do a lot of things, especially fish outside in my spare time. That's out of the way. So I'm going to highlight a couple projects that our research group at the University of Utah is involved with. The first is actually Alex Engstrom's master's thesis. He couldn't be here today, so I'll be presenting this on his behalf. And this is a project that we're working with Keith Hambrecht on, and it's assessing the impact of Phragmites removal on methylmercury in Great Salt Lake wetlands. And while this project is still in its pretty early stages, I do want to share some preliminary results from that study. So, but first, a bit of classic Great Salt Lake background and why it's rather unique with respect to mercury. Traditionally, the south arm of the lake has been stratified, and that's due to this density difference between the south arm of Great Salt Lake and the north arm of Great Salt Lake through the railroad causeway breach historically causes that north arm water, that dense north arm water, to flow into the south arm at depth, pools at the bottom of the south arm, stratifies the lake, has historically formed something that we know as the deep brine layer. And in this deep brine layer, but also just in the anoxic bottom waters of Great Salt Lake generally, regardless of if there's a deep brine layer, there's significant sulfate reduction and generation of hydrogen sulfide. There's very high organic carbon in the bottom waters of Great Salt Lake as well. DOC can reach above 80 milligrams per liter in Great Salt Lake bottom waters. And these conditions are very favorable for any inorganic mercury that has been transported to the lake, it's in the water column or underlying surficial sediments, to be methylated. And that's concerning because methylmercury is the more toxic and bioaccumulative form of mercury. And these concentrations in Great Salt Lake bottom waters can reach rather high levels. They can exceed 30, rather unprecedented, I might add, 30 nanograms per liter, which is some of the highest values ever measured in a natural body of water in the United States, and I think globally. And a high fraction of the total mercury pool exists as methylmercury. Well, that's all great, but you might be wondering, Sam, why are you talking about the deep brine layer and main body of the lake when I'm going to highlight the wetland environments? Well, these same exact conditions, or very similar conditions, occur in wetlands. And wetlands with respect to methylmercury in Great Salt Lake are rather understudied. And this is a video actually from when I was out with Keith and Alex helping them sample. And wetlands are, well, they're biological hotspots for birds, maybe even more so than the main body of the lake. And so when we talk about methylmercury risk to Great Salt Lake biota, we're usually talking about the birds, and the fact that these wetland environments are rather understudied with respect to methylmercury. Well, I think that there's further and important work to be done there. So this project is kind of the first step to potentially addressing that. But what about Phragmites dominated wetlands specifically? What might make those hotspots for methylmercury production? Well, they have dense shallow root structures. It provides organic matter and microbe-rich environments for those sulfate-reducing bacteria to methylate mercury. And I should add, though, that significant methylmercury production has been observed previously in root structures of macrophytes, or just aquatic plants. So this is something that warrants a bit of investigation. There's anoxia and sulfate reduction in shallow pore waters in these wetlands. And Phragmites obstructs wetland hydrology as well. And so that leads to the kind of pool, these stagnant pools forming. There can be stratification at the sediment water interface. And all these conditions are really favorable for methylmercury production. In a project that Bill was involved with, I think that was published in 2015 or 2016, a couple sites that were in Phragmites, he measured some high methylmercury concentrations in shallow pore waters that exceed, I believe, 10 nanograms per liter. And so this kind of sparked Bill's thoughts, and he was wondering, well, maybe Phragmites specifically, these environments are hotspots for mercury methylation. Just the other thing I want to highlight too, it's not always just about mercury methylation. It's about methylmercury degradation. So sunlight can actually degrade methylmercury back into its less toxic inorganic form. And on the left here is an example of a native or a wetland environment mostly dominated by native plants. These plants are less dense, they're less tall, and sunlight can reach these shallow waters. Phragmites, on the other hand, can grow to be like 12 to 14 feet tall. It's really dense. It might obstruct sunlight. So maybe there's less photodegradation of methylmercury in Phragmites dominated wetlands as well. So our hypothesis is that Phragmites removal may actually reduce methylmercury in Great Salt Lake wetlands in the long term. But long story short, the study is still in its infancy. We collected samples in the summer and fall of 2022, before and after Phragmites spray treatments. But this is really the first round of spray treatments in a very, very long process, right? Phragmites removal, and Keith is on this call. He could, I'm not sure if he is. He could probably answer this, but I believe it takes up to 5 years for Phragmites to be eradicated and for these wetland environments to be restored. So with that being said, these first values essentially provide a benchmark, right? And we can see that methylmercury concentrations in pore waters exceed or approach 10 nanograms per liter at a couple sites and are at levels around 1 nanogram per liter over pretty frequently. And those are pretty, well, they aren't deep brine layer levels. They're pretty high levels of methylmercury. That dashed red line at the top is the uncontaminated threshold for methylmercury, the kind of accepted value of, it's only 0.3 nanograms per liter or so. And yeah, these pore water values exceed that, and some surface water values as well. And the last thing that I do want to highlight is that, again, if you have more hydrogen sulfide generation, generally that is correlated with increased mercury methylation because it's a result of sulfate-producing bacteria that are mercury methylators. And we do see a correspondence between our filtered sulfide concentrations in both pore waters and surface waters and methylmercury concentrations around correspondence. Thanks, Chris. I see your question there. Yeah, I should have highlighted the sample map a little bit. Oil drain, so OD is actually at the mouth of the Northwest oil drain. It's a rather contaminated site with respect to a few different trace metals. And it has received refinery and industrial discharge historically. So yeah, I just wanted to briefly highlight this study. But I do want to transition now to talking, and happy to take more questions about this study at the end, but I do want to highlight some of the work that I'm doing for my dissertation and a very large chapter of my dissertation as well. I'm using mercury and lead stable isotopes to assess sources of metals to Great Salt Lake and assess changes in sources over time. So we talk about methylmercury concentrations being elevated in Great Salt Lake wetlands. Y'all might have, if you're at this meeting, chances are that you've seen a lot of headlines related to Great Salt Lake dust, and not only that, metals in Great Salt Lake dust as well. Or you're probably familiar with the mercury consumption advisories implemented for waterfowl that were then updated this year. But with a lot of these headlines, and a lot of these developments, I think that a question that is relatively understudied and somewhat gets overlooked is, well, what is the source of these metals driving these alarming headlines or these consumption advisories and just public concern? So with respect to mercury, I want to highlight potential source pathways to Great Salt Lake. Great Salt Lake can receive inputs from long-range mercury transport from both regional and global sources via direct atmospheric deposition to its shallow waters. And mercury can reside up in the atmosphere 1 to 2 years prior to deposition. So mercury is really a global contaminant. Other sources include local atmospheric emissions and as well as industrial runoff via surface waters. Well, Great Salt Lake is adjacent to the Wasatch Front metropolitan area, a large urban area. And Great Salt Lake is also adjacent to numerous current and historic mining and smelting operations, which is something that I'm going to highlight and touch on throughout this presentation. And next, Great Salt Lake can also receive watershed inputs as well. We're in a snowmelt dominated system, and it receives runoff from both the Wasatch and Uinta Mountains. So how can we potentially distinguish between these source pathways with respect to mercury? Well, enter mercury stable isotopes. They're very useful environmental tracers, and I'm not going to get too into the weeds in this slide, but the right two panels here are examples of triple N-member mixing models that assess the relative contributions of industrial, watershed, and atmospheric mercury in sediments collected from various regions in and around the Great Lakes. The photo on the left is actually an example of, I guess, a binary mixing model that is used to assess the watershed versus industrial contributions of mercury in fish tissues in a study site in the Northeast. And you know, not going to get too detailed here yet, but mercury isotopes are valuable because they can create products like this. And we're building towards something like this in our study of Great Salt Lake. So what did we do specifically? Well, we collected sediment cores from 4 sites in the main body of Great Salt Lake, because sediment cores can be used as records of deposition, right? Sediments are deposited, they stack on each other. It basically forms, it forms a record. And so we collected sediment cores from 4 sites. We sectioned them into 2-centimeter increments, and we analyzed them for mercury, trace metals, and both mercury and lead isotopes. And before I just get into this, I just want to acknowledge some of Wayne's work that he's done on cores collected from Great Salt Lake, and has found that smelting is likely a significant input of trace metals to Great Salt Lake sediments. And I'm not necessarily looking to totally recreate that study, but I do think that the collection of more cores to help reinforce those findings, and mainly the employment of stable isotope analyses on those cores, will help us better constrain sources of metals to Great Salt Lake, and also elucidate pathways that concentration measurements alone cannot. So just with that primer, I just want to put that primer out there first. On our right panel here, we have mercury as a function of depth in 4 sediment cores collected from Great Salt Lake. And peak concentrations generally occur anywhere from about 10 centimeters depth up to 3 centimeters depth or so. And the timing of the differences in depth can probably be attributed to difference in sedimentation rates at the site. So, well, what did we do? Well, we dated the cores to create that record of depositional history. And so peak mercury concentrations in these cores actually correspond to dates of about 1970 to 1995 or so. And these cores were sectioned rather coarsely. The interesting thing about that time of the peak concentration and subsequent decline towards present day values is this coincides with, 1, the closing of some of the mining and smelting operations throughout Great Salt Lake Valley, and 2, at the most prominent one, the construction of a new smelting stack that, 1, probably has better emission controls, and 2, is taller. It's quite tall, as you all probably know, and it's probably more effective at dispersing contaminants away from Great Salt Lake. So that's the mercury story, but we want to be able to say some things a bit more concretely about where that mercury is sourced from, even though the temporal correspondence with some of those events is notable. So we employ lead, a contaminant that is also in regions of mining and smelting. It is also commonly sourced from those activities. So we look at our lead profile now, and lead and mercury show nearly identical temporal trends. That's really cool. Background values that correspond to pre-1930, let's see, I think that they're about 20 times, or peak concentrations are about 20 times that of background values with respect to lead. And they follow the same temporal trend. And furthermore, they're highly correlated. Yeah, here's mercury versus lead. We have a pretty striking R squared and p-value of 0.89 or so. Oh yeah, gold mines in Nevada. I'll get to some of the, I'm actually going to cover some of those more regional sources potentially a little bit later on, but I'm very glad that you brought up potential regional inputs rather than local inputs, because I think that that's really important. I just saw Chris's comment on the screen.
Chris is retiring. We're not happy about that.
That means she can't come to meeting.
No, you can't. You better.
So the correspondence between lead and mercury in these cores is really striking, but we know a bit more. We happen to know the isotope composition of ores that were smelted in this region with respect to lead. And so we analyze these cores for lead isotopes too to further constrain sources. So that's what I'm about to show here. There's a big shift that corresponds with increasing lead concentrations. And that shift from about 19.5 or so in the lead 206 to 204 ratio to about 18-ish corresponds with that increase in lead. And that gray box on the screen is that range of ores, isotopic composition of ores that were likely locally mined and smelted. So it's the isotopes tell the story that lead in Great Salt Lake sediments, or at least the sediment sections with peak lead concentrations, or from about, put another way, from about 1930s onwards, that's predominantly smelting sourced. But we also can employ mercury stable isotopes to probe, to answer questions about potential mercury sources. So we analyze these cores for mercury isotopes as well. And just like lead, there's a shift in mercury isotope signature with increasing mercury concentration. So coupled with the lead concentration data and the lead isotope data, and the fact that lead and mercury are known to be associated with non-ferrous metal production, well, that likely implies a shift from background to smelting sources. But there are a few very interesting notes in comparing the mercury isotope profile and the lead isotope profile. And that is, well, the source profiles for mercury and lead are actually decoupled in more recent sediments, meaning there's a rebound towards background values in the mercury isotopes. And we don't really, and we see very minimal rebound in the lead isotope values, right? And the other thing that I do want to highlight, I know that y'all probably aren't familiar with mercury isotopes that much in this room, but the background values of anywhere from -0.4 to -0.2 with regard to this delta 202, which you can think of as your overall source tracer. That's basically what this delta 202 represents. Those background values are quite enriched relative to other study areas, and those coincide with lower concentrations. And that's really unique. Usually when you have an industrial source, such as smelting, those values associated with industrial mercury are going to be more enriched relative to background, not more depleted. So why are also these background values more enriched? So we can bring in a third tracer. So just to orient you with the slide first, we have our mercury date profile on the left. We have our delta 202 profile in the middle. And again, think of delta 202 as our overall source tracer, right? Now we can bring in delta 200. And what delta 200 represents is it's an atmospheric specific tracer. And it records photochemical processing in the upper atmosphere. So not only is it an atmospheric tracer, but we know that it is a tracer of regional and global inputs rather than just local inputs. Again, delta 200 fractionation with respect to delta 200 only occurs in the upper atmosphere, just something we really want to drive home here. And if delta 200 values are near zero, usually what that implies is another source is diluting atmospheric inputs, such as an industrial source. So with that being said, we see that both background values in delta 202, our overall source tracer, and background values in delta 200, our atmospheric specific tracer, are both relatively enriched in both most recently deposited and pre-industrial, so I think pre-1930, pre-1940, Great Salt Lake sediments. And this is interesting because precipitation is typically enriched in both delta 202 and delta 200 as well. And furthermore, in periods corresponding to the highest mercury concentrations, we see delta 200 values. The graph's a little noisy, but the delta 200 values are closer to zero. So that implies that at peak mercury, it's probably an industrial source. Or put another way, we can use this to assess the relative contributions of atmospheric deposited mercury and industrial deposited mercury. And just one thing I do want to highlight too is that delta 200, our atmospheric specific tracer, and delta 202, our overall source tracer, this correlation between them, the strong correlation, is quite unique. We don't see this in sediment cores collected from other systems. We see it here in Great Salt Lake. That's pretty cool. So why potentially is atmospheric deposition so important with respect to Great Salt Lake? Well, Dave Nafts, a retired USGS employee, estimated that in terms of current inputs to Great Salt Lake, atmospheric deposition constitutes about over 80% of that mercury. And these results, I think, back that up pretty nicely. Great Salt Lake is really large. It kind of goes without saying. It's 90 miles long from tip to tail, has a giant surface area. It's a pretty shallow lake. At normal historic mean lake level, it's only about 35 feet deep at its deepest point. And so this likely magnifies the impacts of atmospheric deposition to the lake. And so in terms of inputs from both regional and global sources, atmospheric deposition is a really important pathway. So just some key takeaways here. Non-ferrous metal production is an important source of lead and mercury to Great Salt Lake. Stable isotopes elucidate source pathways that concentration measurements alone can't. And specifically, it's that, well, atmospheric deposition of mercury from regional and global sources is a very important source to Great Salt Lake. Contrast that with lead. Even though there's a rebound in the lead concentration profile towards present day values, there's not much of a rebound in the isotope values. It means that even though there are less smelting inputs of lead to Great Salt Lake, smelting still probably the predominant source with respect to lead. That's different for mercury, where Great Salt Lake is reverting to becoming an atmospheric dominated system once again. So you might be thinking, cool, Sam, these are just two metals. What about others? Because this isn't really, this is only really a small piece of the puzzle here. Well, we analyzed the cores for other metals too, and I would highly encourage you to check out Wayne's publication from 2020 that also has some dated sediment cores and some very nice concentration analyses on other metals. But here are some profiles of other metals that we analyzed, and we compared them to lead and mercury as well. So these metals such as antimony, zinc, copper, selenium, and not pictured here, molybdenum, cadmium, even arsenic. These are all metals that are known to be associated with non-ferrous metal production. They show very similar temporal trends. Well, these are depth profiles, but I'll get to that. But they show very similar temporal trends to both lead and mercury. And in fact, they're all highly and significantly correlated with both lead and mercury concentrations and the 3 isotope source tracers that I've mentioned throughout this talk. So therefore, that implies that at least the peak concentration of many of these metals is mining and smelting sourced. And the last thing I also want to highlight is that these are depth profiles. Look at what depths that these peak concentrations are occurring. The greatest metal concentrations typically occur in the top 15 centimeters of Great Salt Lake sediments. And that really depends on where you are in the lake too. Depends on sedimentation rates. So this obviously carries, and this is a nice segue into Molly's talk, if lake levels continue to drop, that lake bed gets exposed. We know that the elevated metal concentrations are present in shallow Great Salt Lake sediments. This carries implications for dust. Dust itself is a big issue. Metals in dust is something that's relatively understudied. And you know, I don't want to steal Molly's thunder here because I know that she's going to talk about some potential impacts of metals and dust, but I kind of want to leave you with that thought. And just to end, here is a photo of I think a dust plume from Farmington Bay coming straight into downtown Salt Lake City. So yeah, I guess with that, I think I'll wrap up. I think that's a good stopping point as any. I'd like to acknowledge all my funding sources on this slide. Thanks so much for y'all for having me. I'd like to acknowledge Bill, my advisor, for all his support over the many years I've been a PhD student. I'd like to acknowledge my colleagues at the Utah Water Science Center for their support, especially in my sample collection efforts. And this research really wouldn't be possible with the folks at the USGS Mercury Research Lab as well. And shameless plug, I'm also involved with some studies related to assessing toxicological risk of methylmercury to Great Salt Lake waterfowl, as well as compiling some water use data sets for the Great Salt Lake area as well. And so if you want to contact and chat with me about any of those efforts, I have my contact info on the screen, or feel free to direct me questions about these 2 projects that I'm presented on. Thanks. Take questions.
Thanks, Sam. That was fascinating. And once again, I feel like every day I learn how Great Salt Lake is uniquely unique and presents unique challenges. So I appreciate another perspective on that in regards to Mercury. That was really
Sam, can you give your
fascinating.
contact info back?
Yeah.
So does anyone have questions for Sam, either in the room or online? Chris has a question.
Hi, Chris.
Okay, so hi there. Great presentation. Lots of questions, but I'm just going to stick with 2 kind of points. One is as far as the wetland mercury exposure. One of the things I think that you'll really want to look at is like exposure pathways to waterfowl. We did a study in about 2008 and found that looking at cinnamon teal, which were using certain part of the wetlands in a certain way, they really did not have elevated mercury concentrations compared to like goldeneye and shovelers that were more in the open lakes. So if you're looking at exposure pathways in the wetlands, I think you'll need to be pretty considerate of which species and which areas of the wetlands they use, and potentially coots might be a really good organism for the Phragmites areas. And then the other thing I was just going to say is that Kennecott right now is looking at like doing selenium removal by removing Phragmites. So you guys might want to talk with those guys a little bit and see what they're up to. So that's the only 2 things that I've got.
Thanks, Chris. I appreciate that. And I do want to add for the waterfowl effort I'm involved in with Great Salt Lake. If anybody has access to some common goldeneye, that would be we should chat after this. But I do have numerous northern shoveler and cinnamon teal specimens. So some of the species that you highlighted, we do have access to. So hopefully those data can be used in future studies as well as looking at internal detoxification of methylmercury.
Okay, I can look in our freezers and see if we still got any goldeneye, but with the caveat that they're pretty low. I don't know what that might be. Anyway.
If you happen to have any, I'd love to get my hands on some. So
Okay.
Thanks.
We'll get you some.
Wow.
Wayne, go ahead.
We should chat after.
Yeah, one of your last statements was a concern about the shallow sediments being exposed. I'm looking at the map. It looks like your cores and I know our cores were all in the deepest
Right. And
area
that's
of the South Arm, and that's what paleontologists do because there's more sediments there.
exactly.
Do we have data from shallower cores? And with sediment focusing, there's a tendency from sediment from the shallower parts of it to move to the deeper areas. So it could be considerably different profiles, but I don't know if we have any data.
You're 100% right about that, and I would say Kevin Perry's study does have some spatial data, of course, from the numerous grab samples they collected throughout the playa, and I think especially down south, he noticed that metals were reaching similar concentrations in those superficial exposed sediments from the southern arm of the lake. So yes, thank you for bringing up that point. I think that is really important to note in this graph and is potentially misleading, but there is concentration data from some samples in Kevin's study that I think supports. Yeah.
So I remember one of the conversations that we had about the metals as well as the dust and the human component or intake. And is it still considered that the dust is as bad as in metals that's in it? Are you gonna talk about that, Molly?
I don't. Yeah, I think that Molly is probably the more appropriate person to answer that question. But PM 2.5 on its own is really significant, and the impacts of metals and dust is still somewhat. It's complex, and I would say it's somewhat of an unknown. But I'm not a dust expert. I'm more focused on aquatic processes.
Well, and honestly, the headlines are much more sexy if they have metals in them, right? Than just dust.
Yeah,
but even though dust is bad, right?
Exactly. Couldn't have said it much better myself.
Okay, thanks.
All right, last question.
Has anybody looked at thallium in the lake?
Yeah, I have thallium measurements on my cores, and Molly's been doing quite a bit of work with thallium.
We've at the health department, in collaboration with others, we discovered an issue with thallium in cattle and in a river in the Great Salt Lake watershed. And we were more looking for like where did it come from and upstream and food safety implications and other things directly. But I also have wondered, does that make it into the lake, and could it be there, and what could that mean? So I was kind of hoping to see TL up there, but I didn't see it. I thought I'd ask.
Are you going to be able to stick around for a little bit after the presentation? I might be able to show you this figure, but with respect to thallium.
Oh, that's great.
And I can't remember if I saw a strong correlation between mercury, lead, and my source tracers, my isotope source tracers with thallium. I think I did, but I'll check. I can check that for you after.
And I've been looking to see if this kind of isotopic fingerprinting is possible for thallium. Is it? Oh yeah, we should definitely do it. All right,
well, what a great segue into our next speaker,
Molly.
So a continuation of our dust conversation from the last tech team meeting. Really excited to hear the Cabbage Queen talk about her dissertation work. So Molly, please take it away. Great.
Could you say more about the Cabbage Queen?
Yeah. Don't worry, you'll see plenty. I had to give you, a teaser. And yeah, I don't think I've ever heard somebody say, I really am interested in thallium isotopes right now, just in a meeting unexpectedly. So we'll talk more. I'm not actually going to talk about my thallium isotope work in today's presentation, but that is another aspect of my dissertation, another aspect that's really complementary to Sam's dissertation. So we're kind of like research Great Salt Lake twins. We both work at USGS, and we are both in the crunch time of our PhD programs. So it's very exciting to be able to talk with Sam today. Thank you for having me join the conversation. Like I said at the beginning, my name is Molly. I think I know most of you in here, either through wearing my USU hat. My advisor at USU is Janice Brainey, and we both work with dust and the ecosystem and human health impacts that dust can have downwind from where it is generated. And I'm going to continue our conversation about Great Salt Lake, metals and sediments, and Sam really guided us nicely into that. So keeping it long story short for this crowd, we know that with Great Salt Lake levels where they're at these days, we're kind of trying to figure out to do with all of these exposed dry lake bed sediments that could be eroded and entrained in the atmosphere as dust. And just as we've been saying in the past few minutes following Sam's presentation, exposure to high concentrations of fine dust on its own is a human health concern, point blank. Think shortness of breath, you have coughing, wheezing, you can have exacerbation of existing cardiovascular or respiratory conditions. So that's regardless of its chemical composition. And your comment was totally spot on that. That's actually not, you usually see arsenic in the headlines, right? You don't, I don't know if everybody knows that regardless of chemical composition, exposure to high concentrations of fine dust is no good for us either. But that being the case, for Great Salt Lake, we know from previous work, as well as awesome ongoing work like what Sam just showed us, or like what Annie presented at the last tech team meeting, that Great Salt Lake sediments and dust produced from them contain metals of concern like arsenic and lead. And the potentially additive or synergistic effects of exposure to high concentration of fine particulate matter that also contains metals and also contains other types of contaminants remains pretty unclear. Fittingly, the gap analysis in the Great Salt Lake Basin Integrated Management Plan work plan acknowledges that we still have a lot to learn about the potential impacts that Great Salt Lake dust can have on human health and on ecosystems. And I appreciated the specific call for the development of a dust emissions risk assessment in that gap analysis. So today I'm going to be sharing some new results from one of my dissertation chapters and kind of use those results to initiate an informal discussion of what we as a group might like to see in a Great Salt Lake dust emissions risk assessment. So what could that look like? What information is most helpful for us? And so the main thing that I'd like for you to take away from this short presentation is that a dust emissions risk assessment should take into consideration multiple pathways through which we might be exposed to or impacted by Great Salt Lake dust, whether that's just exposure to fine dust, or a lot of my talk is going to be focused on specifically exposure to the metals within that dust. I think that people are very aware that exposure to dust occurs largely through inhalation or direct ingestion. When we think about dust, we think about it as an air quality issue. So we think about that being a major way we interact with it. But there are a lot of different impacts that dust can have on us. I think probably most folks in this room are aware of some of the Dust on Snow work by Mackenzie Skiles, Otto Lang, Derek Malia, and they have shown that Great Salt Lake dust deposited to Wasatch Mountain snowpack accelerates snowmelt timing, and this has implications for regional water supplies and even for the ski industry. And we know from work by Greg Carling and Colin Hale that not only does that dust accelerate snowmelt timing, it can also deliver metals and other tidbits to the snowpack that when it melts can lead to changes in water quality downstream. Meanwhile, the mobilization of metals from Great Salt Lake dust deposited to food crops has yet to be evaluated. And at least in my opinion, it hasn't really been widely recognized as a potential consequence of low lake levels. And so here it is. This is the thing. I'm coming in with my special cabbage, seeking to deepen our current understanding of the chemical forms and fates. Sam was just losing his mind. This deepened our current understanding of the chemical forms and fates of different metals that are present in Great Salt Lake dust, and evaluating whether food crops cultivated downwind from the dry lake bed might be susceptible to accumulating these metals when the dust is deposited on them. So I'm going to give a pretty abbreviated methods overview here. We collected material for this project and my other dissertation projects using modified Wilson and Cook style wind erosion samplers that we deployed on the dry lake bed of Farmington Bay between 2019 and 2021. As you can see, they're pretty low tech. This canvas flag rotates with the wind direction, and when it's windy enough, dust and sediment blow into the bottle through the inlet tube, deposit in the sample bottle, and then the air flows back out the outlet tube. We left these bottles out there for approximately 1 month at a time. Each field season started typically in May or June, whenever the lake bed was dry enough to navigate. And we'd keep making those monthly treks until the dry season started coming to an end in September or October. And for this project in particular, I composited samples collected from one site that's pretty much in the middle of Farmington Bay over multiple sample periods. So you see that in the map with the star. Briefly, I'll kind of breeze through methods that we use to produce our dust composition and plant tissue composition data sets associated with this project. Before any of the cabbage ballyhoo began, we wanted to assess the relative solubility and human bioavailability of different dust-bound metals. So over in Diego's lab at the U, we subjected 4 different dust subsamples to either 1 molar ammonium acetate, 1 molar nitric acid, aqua regia, which is a mixture of concentrated hydrochloric and nitric acid, and last but not least, a simulated gastric acid mixture. Now, the ammonium acetate targets the most exchangeable and water-soluble fractions of dust-bound metals. The nitric acid targets a slightly less available fraction of dust-bound metals that are associated with feldspar, clay minerals, and organic matter. The aqua regia is what we're using to estimate total metals concentrations in the dust. And then, of course, the simulated gastric acid, which was basically hydrochloric acid with potassium added. We used that to target metals that may induce toxic effects in humans following direct oral ingestion. And we analyzed the metals contents of these supernatants from each of the extractions on Diego's ICP-MS, yielding the first of the 2 data sets from this work, our Farmington Bay dust composition data set. Not having metal samples from in the middle of the lake, but something that's currently exposed. Next, we have the cabbage. I'm happy to answer more questions about the greenhouse experiment itself after the presentation or outside the meeting, but trying to keep things short and sweet as possible. I selected cabbage for this experiment, not just because I'm Polish, but because it has, maybe that had a little something to do with it, but mostly because it has a high leaf surface area, so it can catch a lot of dust. And because brassicas have been shown to hyperaccumulate heavy metals. So cabbage seemed like a good starting point for this research question. Obviously, we eat other vegetables around here too, maybe me less so than some of you. But anyhow, that's how we came upon choosing cabbage. And I arranged this experiment in blocks of 3. Each block had a plant that was randomly assigned as a control. So I didn't add any dust to those plants. And then 1 plant that was exposed to Great Salt Lake dust through the soil to assess root uptake into edible plant parts. And then and my last treatment was a foliar dust treatment. So the plants were exposed to Great Salt Lake dust just by direct application to the leaves, like you see in that picture to the right. I got to just paint on dust storms. So for 65 days, I loved these little cabbages like they were my own children. And then I harvested them. I drove them down to Diego's lab. I washed them thoroughly. I sliced them up. I cremated them, and I dissolved them in acid to analyze their metals content, also via ICP-MS. And so that yielded our second data set from this project, a plant tissue metals data set. And so I'm going to just start really quickly with the dust composition results. What I'm showing you here is just a fraction of what the information that we gained. And this is just showing metals from the EPA's list of priority pollutants. So stuff that we're probably especially interested to know quantities and where it's going and so on and so forth. So In this figure, we have fractions of metals extracted from Great Salt Lake dust by ammonium acetate. That's the blue bars. And an ammonium acetate, again, is indicating how exchangeable or soluble these metals might be. And then we have the simulated gastric acid in the yellow bars. And both of these are plotted relative to their total metals concentrations, which are labeled above each of the bars. And the units are milligrams per kilogram or parts per million. As you can see, stomach acid is much harsher than what we use to assess how soluble a given metal might be in the environment. So the yellow bars tend to be bigger, and you might note in particular that cadmium, lead, and arsenic and Great Salt Lake dust are very reactive to simulated gastric acid. And a takeaway for this figure can be that different metals can pose different challenges for humans or ecosystem health. So for instance, if we zoom in on lead, it's probably something we should be concerned about with respect to direct ingestion. It's very likely to be broken down by our stomach acid. But the exchangeable fraction of Great Salt Lake dust contains very little lead, which means that it's unlikely to be soluble in natural waters or soils. Then in contrast to lead, we can look at something like antimony, and maybe to a lesser extent thallium, the amount of antimony or thallium extracted by ammonium acetate from Great Salt Lake dust are not much lower than those extracted by simulated gastric acid. And that suggests that these metals may present similar levels of risk to human and ecosystems, but of course it also depends on exposure loads. So that's just a little teaser for our dust composition data set. I'm going to move forward with discussing some of the greenhouse experiment results, which I'll preface by saying I was curious whether there might be a difference in metals concentrations in older or younger cabbage leaves, which I thought could lead to some kind of management recommendations, perhaps. So the results I'm presenting to you, you're going to see separated into treatment type. So was it exposed to any dust, and was that dust via foliar application, or was it from me putting it into the soil? And then you're also going to see separation by plant part, specifically old or young leaves. The young leaves were determined from me counting down from the top of the plant and selecting the 5 top leaves and separating those from 5 leaves below it, so old versus young leaves. Something else to be clear about is that I fit our data to generalized linear mixed effects models. So what you're seeing in the following slides are model estimated plant tissue metals concentrations that were informed by what we actually measured in our 6 replicates for each treatment group. So I'm starting with sodium on this slide. Although soil dust exposure, as you can see on the right here, does not appear to affect sodium concentrations in the cabbage leaves in our experiment, foliar dust exposure does increase the concentrations of sodium in cabbage leaves, especially in old leaves. And this is a potential concern for not just cabbage, but other food crops or plants in natural ecosystems, because excessive sodium levels can inhibit plant uptake of water, can reduce plant growth, and damage leaf tissues. So there are some potential concerns associated with increased sodium in food crops or other plants. Next, we found that foliar dust additions can affect the concentrations of things like lithium, antimony, and uranium in cabbage leaves. And these 3 metals were all more concentrated in old leaves than in young leaves, regardless of the treatment type. Foliar dust exposure also appears to increase the concentrations of beryllium and arsenic in cabbage leaves exposed to Great Salt Lake dust, but there was no evidence for a difference between the old and young leaves in these cases. It was just, if it was exposed to foliar dust, then we saw higher concentrations of beryllium and arsenic. And now it's not super surprising to see that these metals and metalloids like lithium, uranium, arsenic can be transferred from the dust to plants, but beryllium was a little bit less expected because it's comparatively less soluble. And so I'm thinking that a likely explanation for this is that some of these metals are entering or interacting with a plant in different ways. And so By that, I mean that the really more soluble metals are able to dissolve in the plant tissues themselves, whereas the less soluble metals are more likely to be sticking around in particulate form and like adhering to plant surfaces, like plant surface waxes, or accumulating in really fine cuticular cracks. So despite really thorough washing, these particulates are really, really, really hard to remove. And there's been a few interesting recent studies demonstrating that fine particles can really stick around in the vegetables that we're eating, no matter how hard we're trying to remove them. And certainly in this experiment, I washed the cabbage leaves far more thoroughly than I typically wash something that I pick up from the farmer's market or from my own garden. So we have some metals in the plant tissues themselves, as well as some metals that are effectively incorporated into the plant, but rather than being in the tissue, maybe they're stuck to the surface. The only metal that, through our experiment, appears to accumulate in cabbage leaves from both foliar and soil dust exposure is strontium, which, like lithium, antimony, and uranium, is more concentrated in old leaves than in young leaves, regardless of the treatment type. And we suggest that this is because strontium is chemically similar to calcium, which is an essential nutrient for plants. This similarity enables the replacement of calcium by strontium during uptake and promotes the translocation to different plant parts. Strontium, there's also just a ton of strontium in Great Salt Lake dust. So maybe there just wasn't enough, was lower concentrations of the other metals, and we really weren't able to detect that transfer from soil to root to edible plant parts. But there's, you know, a few more questions have presented themselves from this. Finally, we did not find evidence that Great Salt Lake dust exposure affects concentrations of selenium, molybdenum, or thallium when the plants were exposed to Great Salt Lake dust, nor did we find that concentrations of any of these metals that I just mentioned vary between old and young leaves. But your next question is probably, well, I'm not hearing you say anything about lead, copper, cadmium, zinc, some of the more ubiquitous metal pollutants. And unfortunately, that's because the fertilizer I used in the greenhouse experiment introduced variable amounts of those metals into different experimental plants. So that was a confounding factor for the statistical analysis, and we'll have to approach using fertilizer differently in subsequent experiments. I suspect that doing so will reveal that more priority pollutant metals like copper and lead may also accumulate in plant tissues in response to Great Salt Lake dust exposure. But for now, we have the sense that several different metals associated with Great Salt Lake dust can indeed be transferred to the edible parts of plants that we are growing throughout the Wasatch Front. And so this brings me to, I know we don't have that much time, and I've kind of just set up the last two slides here with, you know, boring, no more pictures of me like modeling with a cabbage. And I just want to talk about considerations for future work and what we might, what do we want to see in a Great Salt Lake dust risk assessment? So first things first, we need to have additional experiments to understand the transfer of dust-bound metals to plants, whether that's plants in natural ecosystems or stuff that we're going to eat or stuff that we're growing to feed cattle. So in my experiment, I used pure silica sand to grow the cabbage because I wanted to limit any sticking of these dust-bound metals to organic material in the soil. But as it turns out, that also might have influenced the way that we're not really seeing a lot of importance of the soil dust treatment. It's possible that some of the soil or metals were drained out because there were really large pore spaces in the sand. So that might have been a trade-off of using sand in this experiment. I think something that would be really valuable in future experiments would be to use different substrates, especially soils that we would see in the Wasatch Front and throughout northern Utah, to explore how different soil textures, pH, and organic matter contents can affect metals uptake. And then, of course, as I mentioned earlier, we'd want to do this experiment for different plant types. So cabbage is great, but we might want to prioritize looking at other leafy vegetables with really high surface areas. Sam and I have talked about it would be interesting to do such an experiment with alfalfa, given its importance in the state of Utah. You know, we have root vegetables, a lot of different things that we can be looking at here. This was just a first pass. And then another thing I want to note is that in the wild, metals concentrations are going to be, or I'll put it this way. I think that the plants that I grow in my garden have higher metals concentrations for the most part than what I saw in this experiment. And that's because they are exposed to a ton of different atmospheric metals pollution. What I did was I had a closed container basically at the USU research greenhouse, and I only applied the amount of dust that we anticipate falls upon, that we estimate falls upon different parts of the Wasatch Front. And so I only put on Great Salt Lake dust. In reality, plants that we're growing, or the air that we breathe, is influenced from, it contains metals from a variety of different sources, whether those are local sources, regional sources, or global sources, which Sam also talked about. So that's something to keep in mind and motivation for us to consider doing further work in open field experiments, as well as additional closed controlled greenhouse settings that can give us a further understanding of specific effects of exposure to Great Salt Lake dust. I'm going to try to wrap this up right now. So I just wanted to talk about how we can leverage these data from this study and other existing data sets to develop a broader Great Salt Lake dust risk assessment. So considering all of these different pathways, we know that inhalation is an important pathway. So one thing we can do right now is use the dust metals compositions from my data set and multiply those concentrations by PM10 concentrations during dust events. With the caveat being we don't have PM10 monitors right near the lake bed at this time. That's work in progress, and there's discussions ongoing about where those monitors are going to be located. But for instance, I was able to play around with PM10 concentration data from the Salton Sea mitigation program. And so I said, hey, if the concentrations of PM10 during dust events over there are maybe similar to lakeside communities here, this is the amount of bioavailable arsenic we might imagine is being delivered to these lakefront communities, or this is the amount of soluble cadmium that is being delivered to these areas. So we can use existing data sets to make some estimates about what is going on currently or plan for future scenarios. And we can do that in a human health risk framework using an equation like I just kind of threw this up here to fuel our discussion. But we can look at the concentrations of a certain metal in dust, multiply that by an inhalation rate or an ingestion rate. We can use how many breaths per minute do people take, or how much soil and dust does the EPA exposure factor handbook estimate that a person is exposed to on a typical day. And we can multiply that by an exposure frequency and a duration. So for instance, how many dust events do we have per year? Or in the future, how many dust events will we have per year? How many years do you think people are going to be exposed to that? And then if we divide that by the body weight, so that can vary obviously from infants to an average adult, and then the averaging time, which is just the exposure duration in years, that is multiplied by 365 per days. So we can take values for different metals associated with Great Salt Lake dust, and then go on to divide that by reference doses, these doses that are identified by the EPA to be you can orally ingest X amount of lead per day without having negative health effects. And that gives us values that we can then add up for different metals to try to determine, are we at this tipping point for this becoming a concern, or are we not too concerned about this particular metal or these suite of metals or this particular exposure pathway. So we can do this not only with dust, we can do this with contaminated plants if we have an idea of how many like dry weight grams of vegetables that a typical person might be consuming. And another thing that we can do is use other existing data sets from this region, like what Annie presented last meeting, to get some, to just play around with numbers of what is the metals loading to different parts of the Wasatch Front. What Annie presented shows different dust fluxes for different areas, whether we're in Box Elder County or in Davis County, and those fluxes are presented in milligrams per meter square per day or per year. Well, we can figure out how much of that dust is coming from Great Salt Lake through some of the mixing model work she's doing, and then go on to say, okay, well, we know that 40% of the dust falling in this area is coming from Great Salt Lake, and I know that 40% of Great Salt Lake arsenic is human bioavailable. So we have a lot of existing data that we can play with to create ranges for different scenarios of how frequent are dust events, how much dust are you interacting with through the different exposure pathways. And this can really guide our efforts to ultimately produce a Great Salt Lake dust risk assessment. And I'm just going to leave it at here. Hopefully we can have a nice chat about that. And I thank you for all of your time. I thank my collaborators and my funders, and it was really fun presenting with you, Sam.
Yes, well, Molly.
Thanks, Molly. Thanks for letting me coerce you into telling us about your cabbages. It's fascinating to hear it. Also, my favorite word of the month now is follicular, so thank you for that. That's a nice one. So we have a few minutes for questions, either online or in the room for Molly. Anyone? Wayne?
Have you done any of those calculations?
I have, and Annie is doing some of them as well. Preliminarily, in current scenarios, I'm not seeing any alarm bells going off with respect to metals. I'm only looking at metals concentrations in cabbage that I've found to be influenced by additions of Great Salt Lake dust. So, and I was playing around with some other back of the envelope calculations. It's like, oh, you got to eat 72 cabbages in one day to, I mean, there's obviously that needs to be refined.
So you're in trouble.
Yeah, you all are fine. I'm not. Yeah, it's complicated though, because, for instance, for the exposure factor handbook from the EPA, it lists like a maximum of 200 milligrams per day for ingestion rates of soil and dust in the typical adult. That's an upper end estimate. And that is not necessarily what happens to us during a dust event. That might just be like background day to day, like if you like smoke a cigarette, there could be dust on it, or you eat food, there's dust on it, you track in dust to the house in your shoes, you like put something down and you like accidentally like put your hand to your mouth, that kind of stuff. But in terms of exposure during a dust event, I think we need to look at a range of ingestion rates, because if you're just walking around and having a conversation and there's dust floating around, I imagine you're ingesting a lot, both inhaling and ingesting quite a lot of dust. So there's a lot of numbers to still play with.
Mm-hmm. So two things. Great job. I have to say that some of us in this room and online dreamt of a day that we'd have so many graduate students actually studying Great Salt Lake. I mean, we didn't think it was going to happen for a very, very long time. So this is really exciting. So thank you for doing that. The second thing is that, other saline lakes that have dried up have, and I don't know what if it's propaganda, if it's real, you know, some of the things saying, you know, higher cancer rates and the crops are dead and things like that. And so I don't know how, if there's any way we can compare to that type of exposure and accumulation over time to anything that's happening here, because I mean, those are pretty extreme, and I don't know if there is a comparison. Have you looked into any of that? Either one of you looked into any of that? No, I mean, because you're plenty busy.
Yeah. Yeah, I mean, that's a great question. I think probably all of us are concerned about that, and I think we're all trying to work towards more concrete mini answers to that question, I guess. So by looking at different exposure pathways and using a framework such as what I have up there for hazard quotients and hazard indices, we can at least provide some specific answers with respect to specific metals. I mean, we can do this for just fine dust as well, and we can do this for all sorts of different constituents that are bound to the dust. But I think the work here is really young. A lot of the lake bed is recently exposed, and so the more people who are trying to tackle these questions, the better. There's a lot of different angles, and we can look not only in kind of the risk assessment sense, but also in retrospective analyses of emergency department visits that are perhaps in response to dust events. We still don't have a great record of dust events that are specific to Great Salt Lake because our region is influenced by multiple different important dust event or dust sources. So kind of a non-answer, but it's messy and it's still kind of a newer issue. And so I hope to be able to make more concrete statements about how Great Salt Lake dust is influencing different aspects of human health and ecosystem health, but we've got a little bit of a journey ahead of us. What would you add to that, Sam?
Oh, tougher. I'm not sure if I have too much to add to that. I mean, you know, I'm less of a dust expert, and I've really more focused on kind of in-lake processes or biological processes today. I think that this question was, well, I think a point that Wayne brought up earlier after my presentation, I think it's kind of a point, but maybe getting a better sense of space, how constituents in Great Salt Lake sediments, like more of a spatial distribution sense, right? Not just in the lake bed that's exposed, not just in these deep cores, but maybe in these shallow sites that are, you know, that have yet to be exposed, and, you know, maybe kind of assessing the gradient of metal concentrations. Then I think that kind of related to one point that you brought up or were asking about there. But I think as I'm in this dissertation chapter that I'm writing, you know, as I'm tying a lot of my concentration measurements in the cores to kind of implications for dust, and Molly sent me some, you know, nice background references on that. But it also kind of highlighted to me, there's really not a whole lot of work that's been done to date, and there's still a ton of things to do. So I think that what Molly was saying is totally spot on.
Are you saying that it hasn't been done on other lakes either, or just hasn't been done here?
I think Wayne is probably the best person in the room to talk to about this, but I think that other lakes have really similar challenges. Like, I'm thinking of this Salt and Sea health paper that came out in 2020, Jones and Fleck, and they looked at PM10 or PM2.5 concentrations and compared those to lake levels of the Salton Sea. The complication there being that not all dust coming off of a dry lake bed is in the PM 2.5 size range. There's tons of different sources of PM 2.5, so it's more useful to use bigger, you know, it would be better to use like total suspended particulate, but we use PM 10 and that's quite a lot closer. But there's all these different confounding factors that you have to look at, and they assessed like PM 2.5 relationships between PM 2.5 concentrations and mortality, I think from respiratory conditions, and compared those to salt and sea levels. And they found like it was like a small effect size, but a strong correlation between that. But they had to go there. It sounded like they got some tough reviews because they were getting like, you know, oh, what about like increasing automotive activity? What about like agricultural land development? What about wildfires? So all these things that you do have to consider if you're, and that's one reason, one of many reasons why I wouldn't use PM 2.5 concentrations in our region and compare them to lake levels, because there's so many different sources and so much going on. But so I think other lakes have similar problems when they're trying to like maybe assign concrete numbers to potential consequences of lake levels declining. Would you add anything to that, Wayne?
Yeah, I mean, a lot of the work has come out of the Aral Sea.
That's what I was thinking. Yeah.
Increased respiratory problems down there. More data is coming out from Lake Ormea as well, starting to come out. So it is a general problem. Just a comment. I'm trying to remember our data from our Farmington Bay cores, which were difficult because sediments mix and we didn't get good dating on that. But my recollection in what we thought were good dates, that things increased as you went down in the core, and then it looked like maybe a rainstorm or something that washed out our course. But anyway, if my memory is right on that, and certainly in the deeper course, this is the case. We have higher concentrations back before we had high stacks and so forth. If that's true, as we erode sediments off Farmington Bay, we're going to could be getting into higher concentration.
Gross.
That's more
yeah, I mean, that's good to know.
Speculation, but something
totally
to consider what Sam says about getting more shallow cores and stuff.
Yeah, so that's another consideration that we'll have to consider a range of scenarios, not just for exposure frequency and ingestion rates or inhalation rates, but also like, are the concentrations going to be, how much are the concentrations are going to be changing over time?
Great. Well, we got a few minutes left. I'll just read this comment from Annie online. Annie, who spoke about dust at our last tech team meeting. She says, we have a nice Monte Carlo data set for life scenarios that we're applying to dust metal concentrations that should give us some idea of potential life scenarios that carry higher risk. Stay tuned for more on that, or come see the poster at HEU.
Yeah, Annie is in San Francisco right now, presenting some of our USGS dust work, and she's doing some very cool stuff with this, with these kind of exposure framework calculations. So definitely stay tuned.
And if I could just add, I know you mentioned the emergency department visits, and is that correlated with dust? After Annie spoke, I got together with Annie and Molly, and we've had a couple of meetings now between them and us folks at the health department to try to do that, try to correlate lake levels with dust in the air with, or some proxy for that, and emergency department visits for asthma or other adverse health outcomes. We're trying to hopefully link some of those things together as a one way that in which like the health department can offer some data to help inform some of these discussions.
We're super excited about that too.
So this shouldn't dissuade anyone from eating their cabbage, right?
You should eat your cabbage.
It's not 70.
Yeah, just don't eat 70 right now.
You might
stay
die.
tuned as we continue to.
Consequences associated with that.
You might have other digestive issues. Yeah. But do stay tuned and consider that. I think one thing is that we often think about soil health and taking up contaminant from polluted soils, but I don't think a lot of the people I know who are avid gardeners think quite as much about ongoing atmospheric deposition of pollutants onto their garden. So that's just some food for thought. And yeah.
Great. Thanks, Molly. Appreciate you presenting for us. And we've got about 3 minutes left, so I'll just open up the floor to any updates, issues, comments, announcements. Yeah, Laura.
I have one. We held the Great Salt Lake Basin Integrated Plan draft work plan open house last.
Say that 5 times fast.
Just a bit.
It was a virtual meeting. We had representatives from the steering committee present on a panel. It was well attended from a virtual perspective, but it was recorded and it will be posted online here soon. So you can check the website, Great Salt Lake Basin Planning.gov, to review it if you weren't able to make it. And then comments on the draft work plan are due on January 8th.
Great. Thanks, Laura. Appreciate it.
On your 2024 meeting dates, please add the Great Salt Lake Issues Forum, May 8th, 9th, and 10th. Thank you.
Thanks, Len, for that reminder. Any other? Yes, Wayne.
I've mentioned this before, but the 15th International Conference on Salt Lake Research will be held in Turkey. And no, I don't have funds to get you there. That's November 4th through 8th.
Are you going?
I'm obligated. I'm secretary treasurer.
Darn it. For you.
I heard it's on a nice beach in Turkey, so that's gonna stink.
It's on the Turkish Riviera.
Better be.
Anne, did you have a?
I was just saying that Kim actually posted the link.
Yes. Yep. Thank you, Kim. Appreciate it from the online world. Does anyone else? Tim or Ben? By the way, Tim, this might be your first tech team meeting ever.
Yeah.
It is.
So for folks in the room that don't already know Tim, he's our new Deputy Great Salt Lake Commissioner.
Welcome.
We're really excited to have him, and yeah, no pressure, but if you have anything you want to
No, I'll add, thanks, Marisa. One of the roles of the Great Salt Lake Commissioner's Office is to break down silos, make sure that we're coordinating across both all state agencies, with the federal partners, with private partners, districts, local partners as well. So a lot of what I'm doing right now is gathering information, feeding my brain, and trying to figure out where we can coordinate better, where and I'll be tapping a number of people because there's just so many different meetings, so many different groups. And Brian Steed is, as commissioner, he's really only able to stay at the high level. So my role is to live and breathe and figure the Great Salt Lake every single day and figure out how we can make a difference. So we do have we were by statute directed to develop a strategic plan for the Great Salt Lake. We delivered a draft to the governor on the 30th of November. That will become available. There's a lot of things coming together at the same time in November and January. That will be available around January 15th. So that's the date I can commit to because that's what's in the statute. And then, that lines up with Laura talked about the integrated plan. I promise not to call it the other acronym. The integrated plan comment period, same time. And I want to make sure this doesn't conflict with the Great Salt Lake Advisory Council, but there's a newsmaker forum that the Great Salt Lake Strike Team is holding on the morning of January 10th. And so all those different pieces are coming together. And then at the same time, the commissioner and I are trying to figure out where we're going to be making investments in, the legislature provided the commissioner's office with $10 million. There's another $26 million in the governor's budget that we're trying to figure out where to make investments with that funding to make the most difference going. So it's a lot of moving parts. You guys are all aware of this. Just in this meeting, I realized that, the public health implications of this discussion, we should probably have the Department of Environmental Quality in these meetings as well. But I'm going to be tapping a number of people, asking them to probably have another meeting with me on a monthly basis. But if you ever need anything, and Lynn actually texted me, I think this morning or last night, if you need to meet with, if you want to meet with the commissioner's office, start with me. Brian's hard to get. And then I will I'll pull him in when we can, but you can reliably get me right now. And you can't, I told like Candace, Hassan Yeager and others, they can't overschedule me right now because most people don't know my new email address. So it's tdavis3.
Did they make you get a new email
It drives me
address?
crazy. My
Tell me you don't work for
3 at utah.gov. And my old one, because most recently I was the director of the Division of Drinking Water for Utah, was Tim Davis at utah.gov. The fact that they're
Obviously not available anymore. Right?
Yeah, Blake, what he said about that. So
Are
Tim
you willing
Davis,
to give out your
3.
phone number?
Yes, it's 801-247-3940.
Thank you.
Yeah, so if you need anything from the commissioner's office, while it was stood up last and Brian's been on since May, it's really not, he's done an amazing job of balancing 2 full-time positions. But I'm going to be the one who's going to be full-time all day, every day. And I also have a fairly deep background in water policy. So from a public health, from a water rights, from water resources, drinking water perspective.
So glad to have you.
Yeah.
But yeah,
It's here in Salt Lake City or Logan?
I'm here. So I'm upstairs in a broom closet. So literally in a broom closet. So but yeah, if you need anything, a lot of what I am doing right now is just feeding my brain. So like sitting in these meetings are really helpful for me. And I'm happy to meet with any of you at any time to talk about what you're doing and learn from you. So
Thanks so much, Tim. That was an excellent put you on the spot, and you spoke so eloquently. So appreciate you. And anyone else in the room? We're a few minutes over.
I just one thing, just 'cause I think maybe this audience might be interested. So as many of you know, Water Relief Resources filed an application to appropriate on the Great Salt Lake for 225,000 acre feet. We're holding a hearing. I know there's 2 protestants in this room, so I won't speak to it, but we're holding a hearing on Thursday for that application. If you're interested in attending, it's been up in Brigham City.
And it is remote, isn't it, as well?
I don't know if it is remote. I think it's just being held at Brigham City at the Commission Chambers for Blakowski County. It's scheduled to start at 11 a.m.
Thank you, Blake. Appreciate that.
I know Brent's calling right.
Anything else in the room? Ben, I'm not going to put you on the spot either, but sometimes you have something to say.
Nothing important.
Okay, cool. So that said, we have 4 meetings next year. The first one will be February 13th, and unfortunately this room was not available, so we will be in the Core Center for all 4 of those meetings. So I will attach a map with all of those invites if you've never been to the Core Center. It's just a little bit more of a drive out to the back of the DNR campus, or a nice walk if you enjoy that. So more to come with my emails and calendar invites and whatnot, but in the meantime, feel free to reach out to me, Ben, Tim, anyone, if you have questions. And thanks again to Molly and Sam for really awesome, informative presentations. And lastly, happy holidays. Take some time to spend with your family and your friends, and have a nice time. Yeah. So thanks again, and goodbye.
Thank you.
Blake.
Yeah.
I'm going to be.
Sam.
Yeah.
Who was the first study with
So Bill kind of was the study.